Okay, hopefully everybody's weekend was good. Did everybody experience some limits in real life? The answer is yes. Every day we experience limits. Do we have any questions before we get started? I had one question that said there was a bunch of emails about a bunch of homework assignments. There's only one homework assignment, and I just messed up my settings in Canvas, just so everybody knows. There's one homework assignment that's due on next Monday, okay? You also have homework due tonight over limits, okay? So the homework due next week is going to be over stuff we learned this week. So again, make sure you look at it. Let it guide your learning in the classroom, because you're not gonna be able to do all of it after today. You need to be able to look at the homework and see what you need to be able to do and come to class and try to learn that, right? Okay, so an announcement, class will be virtual for everybody on Thursday and Friday. I'm gonna be out of town, and office hours will also be virtual for everybody on Wednesday and Friday. Okay. So are there any questions on any of these things? The homework is up in Canvas. You can go look at it. It's under week 3 module. Go look and see what I have planned for you. The first 2 homework problems you should be able to do already, because they're over infinite limits that we learned last week. Okay. And then the next 3 or 4 problems, hopefully you'll be able to do by the end of today, certainly by the end of tomorrow, okay? All right, there's no questions, Then let's get started. So last week we learned about a limit, which is it is the most fundamental idea that you're going to learn in calculus. Everything else we do is based on this idea of a limit, okay? And so today, and really this whole week, we're going to be talking about the derivative, which in general, it's talking about the slope of a general function instead of just a straight line, okay? But again, the derivative is just based on the limit. So who can tell me just in some words what the limit was? What the whole idea behind the limit of a function was? What do we think? And in the chat, we have an answer. End of a function. Yeah, it's just what a function is doing as we get very close to a point, right? We don't necessarily care what is happening at that point. We care about what's happening close to a point. And the limit describes that behavior, okay? So today we're going to talk about the derivative, and I'm going to give a little bit of history about what the derivative is and why we even care about it. So historically, the derivative came up in 2 distinct problems. And again, I'm going to define derivative in a few slides. So it came up in the tangent line problem, which I'm going to show you in the next slide, and it also came up in the velocity problem, which we're going to talk about a lot this semester. And I actually already showed you when I first introduced limits. I showed you an example where we were calculating velocity. Do you guys remember the running problem where I was calculating my average speed over shorter and shorter intervals? That's exactly what we're doing for the rest of the week. If you can remember that, that's exactly the only thing we're doing for the next 4 days, okay? Okay, so in the tangent line problems, mathematicians and everybody just wanted to know, how do we compute the quote-unquote tangent line to the curve given by the equation y equals f of x? What is the tangent line, you ask? Well, if we're looking at this blue curve here, the tangent line at the point 1, at this point here, 1, and it's about 2.5, right, is the red line here, okay? So this curve right here is y equals f of x for some function. This curve right here, or this straight line, is the tangent line. Okay? It's the line that just touches the curve and then runs away forever. Okay? All right, so why was this a hard problem? Why were mathematicians looking at this problem at all? Well, what do we need for the equation of a line? Who remembers? What two things do you need to know? Yeah, exactly. We need a slope and a y-intercept, or in general, a slope at any point, right? Because given any point on the line, if I know the slope, so here's, if I have some point on the line, if I know the slope is positive, oh, this reminds me, I'm going to upload homework solutions by the end of the day to week 1 homework, okay? So, side note. All right, back on track. So if I have a point on the line and I know the slope, well, the slope is rise over run, so I would go up, and so if the slope was, say, 3, 1, 2, 3, I'd go up 3 over 1, and then I could just draw the line, right? So yeah, you could get the y-intercept, but in general, you could get any point and a slope. Okay, well, a point on the line, especially in the tangent line problem, that's easy. It's just the point of any point on the curve that you're looking at. So presumably you can get that. But getting the slope of the tangent line is a little harder, because what do we need for slope? If I'm looking at a line, how do you normally calculate slope? Rise over run. And to do that, you need 2 points on the line, right? You need to look at any 2 points, rise over run. Well, we took x1, y1, and x2, y2, and rise over run was y2 minus y1 over x2 minus x1. But with the tangent line problem, I really only know 1 point on the line, right? I know that point on the curve, which is also on the line. So this is what makes this problem not quite as easy as just finding the equation of a line in general. Okay. So here's what I just said, but typed out. To find the slope, again, you need 2 points on the line. And then you calculate the slope as y2 minus y1 over x2 minus x1. So who can think of how we're going to try and find the slope of the tangent line? And it's going to involve our favorite new thing, which is limits. So who can think of how we're going to find that slope of the tangent line? If you can't think of it, that's okay. It took hundreds of years. Newton thought about this problem deeply, and only then could he figure out the solution. So, like I said, the answer is going to be limits. Limits are going to rescue us here. It's going to help us to calculate this tangent line, or specifically the slope of the tangent line. Okay, so let's illustrate this by looking at specifically how limits are going to help us. So let's say instead of calculating the slope of the tangent line, I'm interested in the slope of the tangent line at the point 1, comma, about 2.5. So this point is, for the rest of the slides, this is 1, it's about 1, comma, 2.5. It's really 2.7, but we'll just ignore that for now. Admit. There we go. All right, so let's say instead of calculating the slope of the tangent line, I calculate the slope of the line that goes through 1, 2.5, and then here at about 2, comma, 7-ish. Well, what's the slope of that line? Who can tell me? Or how would you calculate it at least? What was it? Yeah, exactly. Just rise over run. So rise, well, that's going to be this distance here. Let me change colors. Rise is going to be this distance here from there to there. So that's what? 7 minus 2.5. And run is this distance here to here. Well, that's just the distance from 1 to 2. And scientists estimate that that distance is 1. So 2 minus 1 is 1. And what does that give me? That gives me, well, 7 minus 2.5, that's what, 4.5? Scientists estimate that the slope of that line is 4.5. Okay, now what's the next step we should take? Instead of calculating the slope of the, this is called the secant line, by the way. This is a secant line. Well, instead of using the points 1 and 2, I could maybe get a better estimate if I use what 2 points? 1 and what? Not 2, that would actually get us farther away, right? Yeah, if I use 1.5, yeah, I kind of want to slide this line closer and closer. I want to slide this point closer and closer. So if we use 1.5, well, then what's the slope of this secant line? Well, again, we're starting at the point, we're going to switch back to black. We're starting at the point, it's about 2.5-ish again. And now this point is the point 1.5, comma, I don't know what, 2-ish. Okay, and then we can calculate the slope of this line. Zoom in to give myself some more room. M equals, well, it's about 4.2 minus 2.5 divided by what? What's the run? Perfect, 1.5 minus 1. Scientists guess that that is 1/2, right? Okay, so you crank out these numbers, and thankfully I did this last night while I was sitting at the kitchen table eating some cottage cheese, and that gives you a slope of about 3.53 if you plug it into your calculator. Ish. Okay. Well, now, again, we could, instead of using 1.5, I could use the point 1.25 or 1.125, and I could keep getting closer and closer and closer until in the limit we get this tangent line here. Okay, so this is the whole idea. Calculate the slope of the secant line for smaller and smaller values of what I'm going to call h, which is just back here. This would be the distance that we're calling h. Okay, so calculate smaller and smaller, or sorry, the slope of the secant line for smaller and smaller values of this h here. Well, I'm just describing a limit, right? I'm just describing taking a limit. I don't care what actually happens when h equals 0, because when h equals 0, you can't really define what's happening, right? But I only care about what's happening for h very, very, very small and very, very, very close to 0. That's exactly a limit. We're describing a limit process here. Okay. So one thing that I liked to do when I was making this was go back really fast. It doesn't really work on Notability. But on your slide, you have these slides on your own, on your computer, just hit back really fast and forward really fast, and you can see a little animation of the tangent line being approximated. Okay, so in the limit, we get the tangent line here. So this is no longer a secant line, but this is the tangent line. Okay? And we're going to find out how to calculate the slope of a tangent line for any nice enough curve. Okay. Okay, are there any questions about that process that I just described? Any questions online? Any questions in class? Yeah, exactly. As someone said, we're approaching that point. That's exactly what's happening. We're taking that approximating point and we're sliding it closer and closer to the point that we care about. Excellent observation. Any questions before we move on? All right. So in each of those last slides, we took the function f of x, which I didn't tell you what f of x was, but for this class, we care about specific f of x's, and we're going to look at specific examples. So we took a function f of x and calculated the slope of the secant line to the point c, f of c. So for us, c here was 1. That was, we were looking at the point c equals 1. That was our base point for every single one of those slides, right? And f of c, again, was about 2.5. And then we calculated the secant line, the slope of the secant line through c, f of c, and c plus h, f of c plus h, right? So again, back here, h was 1. Here's h equals 1. And f of 1 plus 1, so that's f of 2 we were calculating. Here, h was 1/2, and then we calculated f of 1 plus h, so f of 1 plus 1/2. And we keep doing that over and over and over again. Okay. So the slope is defined, the secant line is defined simply by this, right? If I take c, f of c, and c plus h, f of c plus h, well, the slope is just going to be the rise, which is f of c plus h minus f of c. Everybody got that? And then the run, well, c plus h minus c, that's just h, right? So this is the slope of the secant line. Nothing controversial here. Once we have that, then we let h get smaller and smaller and smaller and smaller and smaller. And we get the slope of the tangent line at x equals c, right? For those of you who have taken this class before, for the homework with problems that I ask you to find the derivative using the limit, if you just use other rules that you know, I'm not going to give you credit on the homework, just so everybody is clear, okay? If you haven't taken this class before, then ignore what I just said. But we need to know the definition of the limit, and we need to be able to, the definition of the derivative, and we need to be able to recognize it when it comes up so that we can calculate with it. Okay, so now the actual slope of the tangent line, well, I just described it in words. Here it is written out using math, right? If f is defined, we need f to be defined in an open interval around that point we care about, c. But if f is defined in an open interval around c, where then if we take the limit here, the limit as h approaches 0 of those secant lines, if that limit exists, then that line passing through c f of c with this slope is the tangent line to the curve y equals f of x at the point c f of c. Okay? So this comes up so often that we give this limit a special name, and I've said it a couple of times now. This limit is actually a function in its own right when you replace c just with x. Like you can move c around, right? It's a function just on its own. And so we give this limit a special name, and that name is the derivative of f, okay? So if I say derivative of f, that's the exact same thing as the slope of the tangent line to f at any x value, okay? So interchangeable. The derivative of f is defined, the derivative of f at x. Now, instead of c, I'm putting an x, because it is a function, we can move that point around, right? So the derivative of a function f at x is defined as this limit. We read this as f prime of x. So that's what the little apostrophe means. You read that as prime, okay? F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So again, this is just taking the secant line, the slope of the secant lines, and we're taking the limit as h approaches 0. Are there any questions about this definition? because we're going to be using it a lot. All right, so let's look at, oh, is there a question online? Can you explain H and C? What are they? Yes, so in this previous slide, C was the point that we're taking all the secant lines through. We took all the secant lines through 2 points, right? We took all the secant lines through 1, 0, and then some other point. For us here, C is that base point. C was equal to 1. C was equal to 1, and H was equal to 0.5 there. And so, again, in these secant line approximations, we always had one fixed point, and that point is our C. Okay? Then H is always the distance that we travel left and right to get to the other point on the secant line. Does that help? Hopefully. Oh, and so why are we switching between C and X? Again, because this C, there's nothing really special about 1, 0. C can be moved around. We can take C to really be any point. C could have been here too. We could have done secant line approximations through this point. Okay, and so anytime something can be a variable, we usually don't use A, B, and C. We usually use an X or a Y. So that's all that notation means. It's just, we can think of C as being a variable. And because of that, we're just changing the letter. Okay. Okay. Any other questions before moving on? Oh, and H is the thing that we're letting get smaller and smaller. Okay. So H is just that run value. Okay. So we have our definition of the derivative. Some terminology before we move on. So because we were looking at secant lines, those are average rates of change of the function over certain intervals, right? And then we take the limit as h goes to 0, or in other words, as that interval length shrinks down to 0. So because of this, we can think of the derivative as the instantaneous rate of change of a function. And this is why when you're looking at specifically a function of time, distance as a function of time, we call the derivative the velocity, which is your instantaneous rate of change with respect to time. Okay. The process of taking the derivative is called differentiation, not deriving. Differentiating, okay? So differentiation, not deriving. A function is called differentiable at a point x if the derivative just exists at x, and f is differentiable on the open interval a to b if f is differentiable at every point in that interval. So this is just like continuity. I define continuity in an open interval. Differentiability, you define it in the same way. If you can take the derivative at every point in an interval, we just say f is differentiable on that interval. Lastly, if y equals f of x, we'll use the following notation for the derivative of y. Sorry, there should be an of here. And this is just some different notations that you might see. I already showed you f prime of x. You might also see this dy dx. This is the derivative of y with respect to x. You could also just call it y prime. Okay, this one, again, this is the derivative of f of x with respect to x. So all of these different notations are saying the same thing. Take a derivative with respect to x, which just means use that definition we saw before. All right, so that's enough of that dry theory. Let's actually do some examples here. Let's find the slope of the tangent line to the graph of the function f of x equals x squared minus 7x at x equals 2. All right, so if I draw that, I can approximately draw that tangent line in, right? Here we're at 2 comma f of 2. Well, f of 2 is -10, right? And so you can always kind of eyeball what the tangent line looks like. It's, again, just the curve that looks like it just touches, or just, it's the line that looks like it just touches the curve, right? And then runs away forever. So that line is approximately what we're looking at, right? So what slope, I don't care about exactly what slope that has right now for a second, but does this line have a positive slope or a negative slope? I think I heard it whispered. Yes, shout it from the rooftops. Yeah, it's a negative slope, right? So this is going to be a good sanity check for when we're taking the derivative here, okay? So we know that m is negative. All right, so let's actually calculate this derivative. So we want, we're looking at the derivative of the function at x equals 2. So that's just f prime of 2, right? But looking back at that definition, this is the limit of those secant line slopes. So limit as h approaches 0 of f of 2 plus h. Again, h is the run that we're looking at. Minus f of 2 divided by h. So again, where did that come from? Well, I take x, or c here, in this case, c is 2, c equals 2. And then you take a little bit of a run, h. You could also take it to the left, by the way. And in fact, it's important to take h to consider when h is both positive and negative. But we take h to be small, and then we look at this is f of 2 plus h, right? So I'm just looking at the slope of the secant line through those 2 points and letting h get smaller. All right, well, this is the limit as h approaches 0. This is an issue I saw on the homework a lot, so let's actually work through plugging in 2 plus h into this. So when I plug in 2 plus h, I get f of 2 plus h. I'm going to get 2 plus h. Whenever you substitute something into a function, always put the whole thing in parentheses, okay? So everywhere I see an x, I'm plugging in 2 plus h. So 2 plus h squared, and then minus 7 times 2 plus h, okay? So there's f of 2 plus h minus f of 2. Well, what was f of 2? Yeah, -10, right? We see it right there. So f of 2 is -10, so minus -10. Again, anytime you're substituting anything, put it in parentheses. You can never have too many parentheses. You can have too few parentheses, but you can never have too many. All over h. Okay? All right. How do we expand 2 plus h squared? Well, you could write it out, right? You could FOIL it. So that's 2 plus h times 2 plus h. Did I give myself extra room here? No. So that's 2 plus h times 2 plus h. So this is the limit as h approaches 0 of 2 plus h times 2 plus h. And then minus 7 times 2 plus h. And then minus -10 becomes plus 10, right? Plus 10. All divided by h. Okay, so this is the limit as h approaches 0 of, FOIL this, you'll get first, gives me 4, FOIL outside plus 2h, there's outside, inside plus another 2h, last plus an h squared. And then we distribute the -7 everywhere, so I'm going to get what? -14, perfect, and then what? Perfect. minus 7h, and then plus a 10. All that is divided by h. Okay, then 4 plus 10 is 14, and then I'm subtracting off 14 as well. So all of those constant terms cancel out, right? Boom, boom, boom. Bingo, bango. Okay, so we're left with, this is equal to the limit as h goes to 0, or h approaches 0, 2h plus 2h minus 7h gives me what? Minus 3h, very good. Minus 3h, so again, that was this. So I'll do this in squares, that plus that, oops, minus that. All right, and then h squared is the only thing left, just plus an h squared. Okay, and then I divide this by h. So then what happens? Yeah, I don't, again, so with limits, and this is going to happen all the time with these, we don't care what actually happens at h equals 0, right? We do when we have a continuous function, as we saw, but this function isn't continuous at h equals 0. I need to do some work first, and that work is just canceling some h's. So this cancels with that and one of those, right? Is everybody okay with that? Okay, so this becomes the limit as h goes to 0 of just -3 plus h. And what is that limit? Yeah, just -3. Now this function that we're left with, that is continuous with respect to h. And so we're just left with -3. And that's our answer. We're done. The slope is -3, right? Let's go back and look at what we have. That looks like it could be -3, right? Yeah.
So I guess I'm confused in the part where you get the
-7 and 10. Where we get the -7. Oh, right here. So this comes, yeah, excellent question. Just if we look back at the graph, or you could calculate it, but f of 2 is, well, if I plug into 2 squared is 4, and then -7 times 2 is -14, and that gives me -10. So that's where, yeah, that's where that -10 comes from. That's subtracting off f of 2. And then the -7, yeah, the -7h, that comes from expanding all of this stuff, or distributing everything. Yeah, any other questions? Good question. Okay, so yeah, again, our sanity check that the slope had to be negative checks out, right, with -3. And again, this slope definitely looks like it could be -3. I believe that. So pretty solid work, guys. All right, so let's calculate, instead of just the derivative at a point, let's calculate it. Oh, sorry, anyone online? Let me look here. Yes, excellent question. The derivative, I'm going to show you an alternate form of the derivative. But here, the derivative that we're working with, that h is just the distance from the base point, the c that you're looking at, and the other point that you're using for the secant line slope approximation. So yes, h is always going to go to 0 for this definition. Again, I'm going to show you an alternate form, but if you want to just work with this definition, that's totally fine. Okay, so calculate the derivative f prime of x of the function f of x is the square root of x plus 2. Okay. Well, what's the derivative? F prime of x. Again, anytime you see this, for now at least, for today and tomorrow, until we learn some better or more simple rules. F prime of x, we're taking this limit. The limit as h approaches 0 of f of x plus h minus f of x divided by, again, x plus h minus x, which is h. And again, h is approaching 0 here. Okay, what is f of x plus h? So that's just everywhere I see an x up here, I plug in x plus h, right? So I'm going to get square root of what? Square root of x plus, not just 2. Yeah, exactly. You plug in everywhere you see an x, in parentheses, plug in x plus h. So plug in x plus h, and then plus 2. Okay? I like that sound. That's a good sound to hear. Any questions on why this is x plus h plus 2, f of x plus h? Okay, and then minus, didn't give myself a ton of room here. Let me move this a little bit. Technology. Oops. Come on, what are you doing? All right, whatever. All right, so minus the square root of minus f of x. Well, that's just the square root of x plus 2. That one we don't have to do any funny business. We just write down what we see. Okay, and then this is all divided by h, the run. Cool. Does this type of limit, have we dealt with something like this before? Yeah, how did we handle this before? Who remembers? We multiplied by something special. Yeah, we multiply top and bottom by the conjugate of that stuff that's happening up in the numerator, right? So if this is a, this looks like a minus b, the conjugate is a plus b. So we multiply top and bottom by the square root of x plus h plus 2 plus the square root of x plus 2. Okay, and so it looks scary, but it's actually going to simplify a lot once we do that. So I'm going to multiply is x plus h plus 2 minus square root of x plus 2 divided by h, and then I multiply top and bottom by square root of x plus h plus 2 plus the square root of x plus 2. Top and bottom, you got to do it to both. All right, so why do we do that? What do we get up top when we do that? What was it? Yeah, exactly. The whole reason we do that is because when we do a minus b times a plus b, we get a squared minus b squared. And that's going to do us a favor in getting rid of the square roots, right? So I'm going to get a squared. Well, that's this guy, all squared. So that's just going to be what's under the square root, right? X plus h plus 2. So this is the limit as h approaches 0 of x plus h plus 2. And then I'm going to get minus b squared. Well, for the same reason, it's going to give me minus, this squared is minus x plus 2. I'm putting it in parentheses so I don't accidentally mess something up. All divided by, so that takes care of the whole multiplication in the top. Okay. So on the bottom, there's not much to do. Square root of x plus h plus 2 plus the square root of x plus 2. There's not much I can do with that multiplying h. You could distribute it if you want. I'm not going to. because I know that I'm going to get a little bit of cancellation. So with these multiplied by the conjugate problems, it's the one time I'm going to say don't simplify and distribute the denominator before you're done, because you're probably going to get some cancellation. So leave it factored. All right, so what happens in the top here? Yes, perfect. Yeah, what happens in the top? Well, I'm subtracting x plus 2, but do I see an x plus 2 anywhere else in the top? Yeah, there's an h between there, but I mean, it's all addition, so I can move the h around, right? So this is really x plus 2, and I'm subtracting this x plus 2. So these guys will cancel, and I'll just be left with h in the top, right? So this is the limit as h approaches 0 of h over h square root of x plus h plus 2 plus the square root of x plus 2. Okay, now what happens? Yeah, perfect. These h's cancel, so I'm just going to use the eraser postulate. That's a funny joke. And put a 1 there. And now, what can we do? What would you like to do? At every step of the way, what would you like to do when you're taking limits? All this work is hard. It would be way easier to just do what? Yeah, exactly. You should always check and see if you can just plug it in, right? If you can just plug in with an algebraic function like this, if you can just plug in h equals 0 and you don't get division by 0, then you're good. That's your answer. That's what we learned with continuity, right? With algebraic functions, rational functions, polynomials, all of that stuff. If you can plug in something and it doesn't give you division by 0, then that's your answer. So when I plug in h equals 0, well, in the bottom, I'm going to get 1 over the square root of x plus 2. I'm going to get 2 of those, right? So I get 1 over 2 square root of x plus 2. Again, when h goes to 0, I'm just left with 2 square root of x plus 2. So that's where that 2 comes from. Okay. So this, in case it's unclear, is my answer. 1 over 2 square root of x plus 2. Are there any questions on any step we did here? And hopefully you guys see, I mean, this is why I've been assigning problems that, yes, excellent, Saba, thank you. Hopefully you guys see that I've been assigning problems that look very similar to this, but we haven't explicitly said compute the derivative. But you've been doing problems like this on your homework at least a little bit. So the actual mechanics of this is not too new. Just the ideas behind it are a little bit new. And the words, derivative, yeah. So, all right, one more example. Calculate the derivative f prime of the function square root of x plus 2. Well, what's gonna, wait, didn't I just do that one? Wait. Oh, I just included the graph there. I'm sorry. Sorry, that graph was to help you look at the slope. My bad. All right, so next example. Sorry about that. Calculate the derivative of f of x is 3 over x. And I believe I included a graph again. Yes, there we go. All right, so we're going to compute the derivative of f of x is 3 over x. This is what 3 over x looks like. So again, you should always remember derivative. All that word means is slope. So it's going to help us to think about the slope at any point on the curve later as a sanity check to make sure what we're getting makes sense. Okay, so if I look at slopes as x approaches 0, they're actually blowing up, right? So that's a key thing that our derivative should have. A key feature is that the derivative should blow up as x approaches 0. All right, so let's calculate this derivative. Well, again, what is the derivative? F prime of x for any function is what? Someone tell me what I need to write. You guys are experts now. F of x plus h minus f of x over h. And then what do I do with this? Careful, there's one very important part that we're missing here. Yeah, we need the limit. Yeah, the limit as h approaches 0. Perfect. Perfect. Okay, so f of x plus h for us is 3 over x plus h, right? This is not 3 over x plus 3 over h, in case anybody wants to simplify it that way. Okay, and then f of x is just, again, 3 over x. So let's plug everything in. This is the limit as h approaches 0. F of x plus h is 3 over x plus h. Minus f of x, well, that's minus 3 over x. And that's all divided by h. Okay, have we seen any limits like this before? Yeah, I've been tricking you guys into doing derivatives this whole time. So how did we deal with this limit before? Well, no, not that way. I know what you're talking about. No, not that way. How do we do this limit here? Yeah, exactly. We not by the reciprocal exactly, but we need. Yeah, exactly. We need to get a common denominator. And again, in previous classes, you probably learned the least common denominator. No, just multiply the denominators together. There's your common denominator, right? So this is the limit as h approaches 0. Well, I'm going to multiply top and bottom here by x, and top and bottom here by x plus h. Okay. And when I do that, I'm going to get 3x minus 3 times x plus h all over x times x plus h. And that's all divided by h. Did I lose anybody there? Okay, what happens in the numerator of the numerator? Perfect. We distribute this negative 3. We're going to get the limit as h approaches 0 of 3x minus 3x. And then what comes next? Perfect. Minus 3h. Divide by x times x plus h. And then I'm dividing by h over 1. So I could, that's the same thing as multiplying by 1 over h, right? So times 1 over h. Did I give myself extra room? No. Okay, what happens with the 3 x's? They cancel. So again, I'll use my good old eraser postulate. Oh, that joke kills. Then now what happens? I've got minus 3h, and something like this is always going to happen with these types of problems. We're going to get, what can I do with the minus 3h? The h's cancel, right? So this, I still have minus 3, but that h cancels with that h, right? And so cleaning up a little bit, I'm just going to erase that, I was left with minus 3 in the top. And so now what happens as h approaches 0? Yeah, perfect. Now there's no issue. After that cancellation of the h, there's no issue with plugging in h equals 0. Okay, and so when I do that, I'm going to get -3 over x times x plus 0. Well, what is that? Yeah, just an x squared. Perfect. -3 over x squared. And yes, if you've taken this class before, you probably knew that already. But it's good to be able to calculate this with the definition of the derivative. Okay, so I'm going to end there. There's more slides, but I expected to have to stop before the end. Tomorrow, we're going to talk about when the derivative fails to exist. We saw a bunch of examples where it does exist here. So we're going to talk about when the derivative fails to exist and how you can tell that from the graph of a function. Okay. All right. If you don't have any questions, feel free to please wipe your desk down as you leave and then head out. Anybody online, if you have any questions, you can stick around and ask. Other than that, feel free to head out and have a good day.